is an elusive concept. To fully grasp a word meaning, it is often helpful to look at etymology. The Old English word from which truth derives has a slightly different meaning. Rather than truth as we know it, this Old English word means faithfulness, constancy. Incidentally, this is the same word that gives origin to the Dutch word for marriage. A paradox that has puzzled mathematicians for millennia is liar's paradox. The paradox that occurs when a liar states that she or he is lying. Experts have never agreed on the way out of the trouble despite over 2,000 years of attention. The paradox is equivalent to stating, this sentence is false. The problem is that, if we assume that the sentence is true, then it becomes automatically false, and vice versa. A paradox. But what is exactly a liar? And what does exactly mean to lie? One possible solution to these questions can be found in probability theory and in its subfield studying stochastic processes. These are processes that stem from repeated observations of random events. But what is a random event? Consider the action of tossing a coin. This action may produce two possible events. Head is observed or tail is observed. If we repeat the action again and again, multiple scenarios may be observed. These scenarios are typically represented as a scenario tree. For instance, the highlighted scenario represents the case in which a tail is observed in both the first and second toss. This other scenario represents the case in which a head is observed in the first toss and a tail in the second toss. Scenario trees, also known as probability trees, are useful to depict the future. However, they do not model actions of an agent interacting with the world. Decision trees do. In a decision tree there are square nodes, representing actions, and round nodes, representing random events. Let's now apply decision trees to liar's paradox. The resulting decision tree depicts all cases that may occur. For instance, a person may claim, "I am not lying," and the reality is that this is not a lie. This means the person is telling the truth. Or a person may claim, "I am lying," and the reality is that it's not a lie. This means the person is lying. Surprisingly, when we analyze these scenarios that may arise, there is no paradox. By separating persons' actions from the actual state of affairs, we obtain scenarios that depict a comprehensive picture of all cases that may occur. It is now interesting to observe what happens if we map probabilities to random outcomes. If a person lies with probability 0, clearly, this person is not a liar. The person will always tell the truth. However, in our decision tree, this leads to an inconsistency. If the person states, "I am lying," since this person lies with probability 0, the only possible outcome is that this is not a lie, which is a contradiction. A similar inconsistency is observed for a person who lies with probability 1. Moreover, if a person lies with probability 1, this person is also not a liar. The person will never tell the truth, but it will predictably do so. Persons that lie with probability 0 or 1 represent limiting cases leading to contradiction. To be truly a liar, a person must try and create messiness. Technically speaking, the liar must maximize the entropy of this stochastic process. From an observer's standpoint, the person must tell the truth with probability 0.5, that is 50% of the times. It becomes clear then that truth has got something to do with the nature of the process underpinning the problem. Truth is a matter of faithfulness, constancy. A liar that always lies is not a liar. Finally, what happens if the probability of lying is neither 0, 1, or 0.5? This is in fact a known case. It is the classical example of decision-making with experimentation. A typical example is pregnancy testing. Pregnancy testing devices that can be purchased in pharmacies are imperfect testing machines. They have a probability of giving false positive and false negative results. Nevertheless, this probability tends to be low, and these tests certainly perform much better than a purely random guess. If a scientist comes up with a particularly bad device, one that consistently returns a negative results when the person is pregnant, or vice versa, the problem can be simply fixed by relabeling test results. In fact, for this test, not pregnant actually means pregnant. Once more, a liar that always lies is not a liar. In day-to-day life, we often rely on imperfect testing machines. They are useful, since they provide us with valuable information. We may conclude by saying that if one lies less than 50% of the times, then it is either a consultant or an imperfect testing machine.